So today we are going to do lecture 17. Where we will discuss more about the row space, column space, all the four subspaces. But let me first recall a question that I had posed last time. The question was something like this. Is there a matrix A such that the null space of A has zero, 1 as a basis and the column space of A has 1, 1 as a basis. Then we'll change this question and we'll go with other things also and see what happens. Now, when we say null space has this as a basis and column space has this as a basis, so we know one thing, that A, it has to have columns which are of the form 1, 1 or a multiple of 1, 1. Since the null space is 0, 1, so for example, if we take something like this, I claim that this matrix satisfies all that we really care about. 0, 1 is 0, 1 a null space or not? Let's try and see what happens. So what is the null space of this thing? For null space, I need to find all those x in R2 such that AX gives us the 0 vector. Okay, so let's try and see what happens. Here is my matrix and here is my right hand side. So I'll try to solve everything in one go and let's see what happens. This will give me 1, 0, B1, 0, 0, B2 minus B1. So when I solve this augmented system, what I see is one pivot, one free variable. So, and for consistency, I need B2 to be equal to B1. So in some sense, I'm going to answer all the questions in one go. What is the null space, column space, and do they satisfy the conditions we are after? So what is the null space? Well, if you look at the homogeneous system, this guy is now going to look as x1 times 1 plus 0 times x2 equal to 0. And the second equation will read 0 equal to 0. So this means x1 has to be 0. So the null space of A would be all the vectors of the form 0, x2, where x2 is any real number. Okay. Now, once we see this, this confirms our suspicion that null space can be generated by the vector 0, 1, or it has 0, 1 as a basis. Likewise, for column space, consistency forced us into this situation. So we can say the column space of A would be all those vectors B1, B2, such that B1 must be equal to B2. Or in other words, we can say this is going to be all multiples of the vector B1, 1, which again confirms our question about what were we after, that the column space has 1, 1 as a basis. So this is how we could have guessed the matrix, we could have generated the matrix. The question could be, is this the only matrix which can do this job? Well, can I change the number of rows or number of columns, for example? I can't change the number of columns because my null space has to be spanned by a two-dimensional vector. So I can't have more than 2 columns. What about the column space? Well, column space has to be generated by 1, 1. So it has to be 1, 1 or multiples of 1, 1. But apart from that, can we say something? For example, is this the only matrix, or could A be something like this? Just a matrix of this form, 1, 1. Could it be? Well, if you think a little bit, A cannot be of this form because then it doesn't satisfy the null space criteria. So if somebody says, is this the only matrix which can do this job? The answer would be no. Because instead of 1, 1, I could have easily used 2, 2 or 3, 3 or any like 2 numbers equal to each other. So in general, I could have used a matrix of this form, A, 0, 0, where A could be any real number that I want except 0. So there could be a lot of matrices, but all of them will sort of look like this. And it kind of corroborates the rank nullity theorem that we talked about. Null space has dimension 1, column space has dimension 2. So the domain space of this can only have dimension 2. So let's take it from here and see if we make a small change in this question, whether that change will make things different. So what if I change this question, and instead of saying is there a matrix A such that null space is spanned by that vector, I'll make one change here. Pretty much the question remains the same, but now I want the row space of A to have this as a basis. Okay. Can such a matrix exist? So let's try to see what are we after. We are saying that a matrix, whatever it looks like, the rows are spanned by 1, 1. So it should be something like this. Out here, I can have a multiple of 1, 1. I can have another multiple of 1, 1. So like, as long as my matrix is of this form, it at least satisfies the second condition that the row space has 1, 1 as a basis. What about the first condition? How about the null space? Can this thing has 0, 1 as a null space? So what it is saying is, if you have a column like this, 1, A, B, C, can you multiply it by 0, and you can multiply the second column by 1 to produce the 0 vector? Can it happen? Well, as you can see, it cannot be true because the first coordinate is 1. Even though the rest of them could be 0, but there's no way that we can produce a linear combination of 0 out of this. So our suspicion is that null space cannot be generated by this, or there cannot be a matrix which satisfies both these conditions to be true together. Now, question is, why did I bring this question here? I wanted to emphasize on one thing, which is not very obvious unless you think about it, and then it becomes fairly obvious. What is the relationship between a null space and the row space of a matrix? Let's take a look in general. When you say, I'm going to find the null space, so for null space, you're going to solve this equation for this system. Okay. Any x that you find that can satisfy this equation, you will call it as a null space vector. But let's try to look at slightly from a different perspective. Suppose these are the rows of my matrix A. And let us say this is a vector that you have found for your null space. And you want to produce a zero vector. So this is your A. This is your vector in the null space of A. Now, based on the matrix multiplication, when you multiply the matrices, what exactly do you get? You'll say R1 dot X, R2 dot X, and so on and so forth. And you want this guy to become equal to the zero vector. This means what exactly are we getting? We are saying that Ri dot X must be 0. Ri dot X must be 0 for all I. This means each row of my matrix A is orthogonal to any vector from the null space of A. Now this gives us a very interesting relationship between the row space and the null space. We can say these are orthogonal spaces because every row is orthogonal, so anything spanned by that will also be orthogonal. So what we are now claiming is that the row space of A is orthogonal to the null space of A. Now, once we know this result, then we could have easily come over here and answered the question that such a cannot exist. Because if this is the basis for null space and this is the basis for my row space, they can only be possible if they were orthogonal to each other. And 0, 1, if you take this dot product with 1, 1, it is not going to be 0. So you know that such a matrix cannot exist. So in terms of geometry, if somebody says, can you find me a linear transformation such that this is the row space and this is the column space, this is the null space. It is not possible because the angle between these two spaces is not 90 degrees. Okay? This is a nice relation which is of advantage to us. Maybe it's not very apparent what the advantage would be right here, but later on when you deal with these things a little more, you will see there's a distinct advantage of having something like this. So we deal with things like projection and all. So now we can talk about the row space in a slightly different way. The question is, what is another way of looking at the row space? Well, remember we are very fond of linear transformations. So suppose I have a m by n matrix A. This can be thought of as a linear transformation from Rn to Rm. Okay. Now, when you say row space, can we also say that the rows of A are actually the columns of A transpose? So when you deal with A transpose, it would be a n by m matrix. So this would be a linear transformation from Rm to Rn. And based on this, you can easily see that the row space of A is nothing but the column space of A transpose. This kind of relationship in math is usually called duality. We can't go deeper into the concept of duality, but anytime you go in advanced math, you will see this concept coming up quite a bit. These kind of relations that we can exploit help us change our viewpoint and try to answer questions slightly differently and then recover our answer of the original question. Based on this, it's now one thing that one can obviously ask, what about the null space of A transpose? Since A transpose is a linear transformation, what about the null space of A transpose? Well, let's see, what would exactly be the null space of A transpose? Suppose I tell you that the vector y belongs to the null space of A transpose. This means A transpose times y would give me the 0 vector in Rn. Okay. Now, using the properties of transpose, I can say this is A transpose y whole transpose should be the transpose of the 0 vector. Okay. Okay. What does this give me? Using the properties of transpose, I can write this guy as y transpose, A transpose transpose, which will be just the vector A, is this. So basically what we are saying is that if something belongs to the null space of A transpose, that vector when multiplied to the left of A will give me the 0 vector. So this is what is the concept of the left null space of A. Left null space of A is actually nothing but the null space of A transpose. This is how we define the left null space. I just wanted to emphasize why the word left has been involved there. It's because you're multiplying, if you look at the matrix A, you're multiplying a vector on the left to create the 0 vector. Now, the rank nullity theorem can be applied to anything, any linear transformation. So by the rank nullity theorem, we can have both of these things true, which is that the rank of A plus the nullity of A should be equal to the dimension of the domain of A, which in our case turns out to be N. But I can apply the same thing to A transpose. The rank of A transpose plus the nullity of A transpose should be the dimension of the domain of A transpose, which in this case turns out to be N. Now keep in mind that the rank of A, how did we define the rank of A? Number of pivot columns or number of pivot rows. In that case, since the rank of A must be the same as rank of A transpose, let's denote this number by R. This tells us that now we can talk about the nullity of A. Nullity of A would be N minus R. Nullity of A transpose would be M minus R. So one can ask these kind of questions. When will both the nullities be the same? What are the consequences of that? But these are some things which can help us understand the structure of these linear transformations a bit better. And this is what we are after. So what I'll do is I'll try to solve one problem based on how to find the row space and the left null space. That will help us understand the mechanics of it. Now, before I solve that example, let me also illustrate something might be of some use to us. So imagine A is a transformation from Rn to Rn. Now, the null space of A sits inside Rn. So imagine this is where your null space of A is. This is the so-called null space of A. Then you said the row space of A also sits inside Rn, or you can say the column space of A transpose sits inside Rn. But remember, the row space and the columns and the null space are orthogonal to each other. So this is a 90-degree angle, just to denote that idea. So here we have the row space of A, which is the same as the column space of A transpose. Okay. Likewise, if we go in Rm, remember the column space of A will be living inside here. So this would be the column space of A. Column space of A should be the same as the row space of A transpose. So the null space of A transpose and row space of A transpose should be again orthogonal to each other. And this is how you will see that the null space of A transpose is living in here. Okay. So this is the kind of picture you should have in mind when you deal with these spaces. Now, in general, null space and row space, they will have at least something in common. I'm not saying this is the only thing in common, but they could have more things in common, but definitely they will have something called the zero vector in common. Because being a subspace, they would definitely contain the zero vector. So null space basically take anything in here, it maps to the zero vector over there. Null space of this thing maps anything in here to the zero vector over here. And the rest of the story continues with the column space. The point out here that I'm trying to make is that Rn is made up of these two spaces which are mutually orthogonal. So in some sense you have taken Rn and you have partitioned it into two mutually orthogonal spaces. So what we are saying is, you pick any vector in Rn, I can write it as a sum of a vector in here and a vector in there. This kind of splitting is what we call as a direct sum under some circumstances, and it's of great use in general. Those of you who have taken physics, you might recall that whenever you are given a body and a force is acting on it, you try to break it into components which are mutually orthogonal. Question is, how do you know it is always possible in any vector field? And think about these things and you will understand why such a split is always possible. And the good part of splitting it into orthogonal components is that on its own, those components do not interfere with each other's action. So you can just look at one component and totally control its action. Look at the other component, you can control its action without any interference from the other guy. So these kind of splits are usually very helpful. Okay, so now let's try to do a simple example and see how does it help us. So here is a matrix, and I'm also giving a echelon, row reduced echelon form of it also. So here's my matrix A. It's a rather big one. So here's my matrix A, and its row reduced form is the following. So suppose somebody says, I want to find the row space of A, or let's say a basis for row space of A. Then somebody might ask, I need a basis for the column space of A. And maybe a basis for the null space of A transpose, and maybe a basis for the column space of A transpose. Okay. Now, one way is we can do all these problems individually and keep on repeating the same thing. Otherwise, we observe something here. Row space of A is the same as the column space of A transpose. So basically, these two questions are one and the same. If you say basis for row space of A, it's also giving you the basis for column space of A transpose. What about if somebody says, I need a basis for the row space of A transpose? Well, row space of A transpose is the same as the column space of A. So those two questions again are the same. So technically speaking, what we are after should be only the following thing. These are the only questions basis for that we should be answering. Rest of them will follow fairly easily. These four questions are the ones which we should be answering. Okay, so let's go with the easy things first. Do I know the basis for row space of A? Remember, the row space of A, we can use the pivot columns in here. This is a pivot column and this is a pivot column. So we can use the pivot rows from here to give a basis for the row space of A. So one of the bases we can give is basically 1, 4, 8, 0, 5, the first row of my reduced matrix, or the third row of my reduced matrix. Now here's a simple question. Can I come here and say, well, this would be my pivot row from here, and my third row would be a pivot row in A? Not necessarily, because we don't know how did we do this reduction. I might have swapped the rows. So if you know all the swaps that you have made, in that case you just backtrack the swaps and figure out which of the rows are giving you the first and the third row. If you made no swaps, then you are okay. Then the first row and the third row form a basis here, then the first and third row will form a basis here also. So keep in mind that swaps can change the order of the rows. So in some sense it is much more convenient to deal with the reduced form and talk about that. But when it comes to the column space, life is a little difficult. Remember, we figured out that the column space of the reduced matrix need not be the same as the column space of my original matrix. However, it does tell me which columns are my pivot columns. So for example, in this case, my third column is a pivot column. Sorry, my fourth column is a pivot column and my first column is a pivot column. That information remains unchanged. So I can come here and claim that, well, these are the things which form the basis of my column space. So as you can see, the row space is two-dimensional, the column space is two-dimensional. That better be the case because remember, rank is the same as the number of rows, number of independent rows or the number of independent columns. Now I can talk about the null space of A and the null space of A transpose also. First, let us deal with the null space of A. How do I find the basis for the null space of A? So how will I find the null space or the basis for the null space of A? Well, all we need to remember is the following thing, that the solution set for Ax is equal to 0 is the same as the solution set for Rx equal to 0, where R is the reduced form. So this is our R, and this is our A. So the solution sets for both of them are going to be the same. So it will be easier for me to find the null space from there and see how things go. And then that can give me the basis. Okay. Remember, null space is controlled by the free columns. So I want to figure out how to deal with those free columns and how can we use them to our advantage. Okay, so let's see. If you look at the reduced system, it will look like x1 plus 4x2 plus 8x3 plus 0x4 plus 5x5 equal to 0. And likewise, we will have other equations, 2x2 plus 5x3 minus x5 equal to 0. And what else do we have? We have x4 plus 4x5 equal to 0, and then 0 is equal to 0. Let me actually remove this from here so that it's easy for us. Now remember, x1 and x4 are the pivot variables. So everything has to be expressed in terms of the pivot variables. So for example, we can say x5 is minus 1 over 4 x4. Once we get x5, we can deal with the rest of them and try to make sense of it. Let me see. What am I trying to accomplish? I had a slightly different idea in mind, but nevertheless, let's proceed. Okay, so I got x5, then I will have everything in terms of 4x2 plus 8x3 is minus x1 minus 5x5, which is the same as saying it is minus x1 plus 5 over 4x4. So as you can see, I have expressed x2, x3 also as a linear combination. Then from the second equation, I will have 2x2 plus 5x3 is equal to x5, which is the same as minus 1/4 x4. So from here, you can try to find out whatever x2 and x3 are and find the answer to the null space. So let's try to gather, there are a lot of equations floating around. Let's try to gather this information in an organized manner. x1 and x4 are free variable, pivot variables. Everything else is free. Okay. I'm trying to find a simpler way to deal with this. So let me deal with it in a slightly different manner. You can do this exercise in a longer way, but I want to do it in a shorter way. So let's try to be a bit intelligent about before writing down all the solutions. I'm trying to figure out what linear combination of those guys can produce me a 0. So, for example, if I look at this vector, 0, I'll put something in the second and the third in a moment. And say 0 and in here. Can we say that anything which lives in the null space has to be of that form? That means the first entry and the fourth entry would definitely have to be 0. The reason for that is those are linearly independent columns that we have. So the only combination that can help us deal with those would be 0. So that is one way of dealing with it. A possible vector in the null space could be of this form. So question now is, what is the dimension of the null space? Here we will use our rank nullity theorem. Dimension of the null space of A would be the number of columns minus the rank of A. And I think we have already found the rank of A to be 2. So we know that the dimension of the null space has to be 3. So there should be 3 basis vectors which can possibly give us what we are looking for. Question is, what are those 3 basis vectors that we can get? And that is what we can achieve by solving this system of equations. Okay. Now, the numbers are not that neat that I can show you a small technique that works quite efficiently. However, I'll see if I can somehow reduce the number of calculations for us. So let's try to do the following thing. Let's try to solve for the pivot variables in terms of free variables, not the other way that I mentioned a little while ago. So x1 would be minus 4x2 minus 8x3 and minus 5x5. And x2 would be, sorry, what is the next? x4 would be rather. x4 would be minus 4x5. Okay, great. So how would a solution possibly look like? x1, x2, x3, x4, and x5. This will look like minus 4x2 minus 8x3 minus 5x5. x2 remains x2, x3 remains x3, x4 is minus 4x5, and x5 is x5. So now we can split it as minus 4, 1, 0, 0. x3 would be minus 8, 0, 1, 0, 0. Then we will have x5 times minus 5, 0, 0, minus 4, 1. Now, as you can see, based on the position of zeros, it's kind of clear that not any of these vectors can be expressed as a linear combination of the other two. For example, can this vector be expressed as a linear combination of these two? If it was, these two will have the last entry as 0 no matter what I multiply with. It can never give me 1. So this is independent of these two. Likewise, can these two combine to produce this guy? Look at the third quadrant. They both have zeros. They cannot produce 1. Can these two combine to produce this guy? In the second quadrant, both of them have 0. Out here, second quadrant, we have 1. So there's no way that any of them can combine together to produce the third vector. So these are three linearly independent vectors, and hence they form a basis for the null space of A. So basis for a null space of A is of the form minus 4, 1, 0, 0, 0, minus 8, 0, 1, 0, 0, and minus 5, 0, 0, minus 4, 1. This is one of the bases of a null space of A. Okay. We can also find the null space of A transpose using similar ideas and doing the row reduction of A transpose instead of A. So I'll leave that as an exercise for you. But the dimension of null space of A transpose can be easily found. It would be 2 based on the rank of A transpose.
46 minutes.
Then we can cut at this point and start the new lecture.